shut off, huh? So, um, initial velocity of the wooden block, it says is rest, therefore 0 meters per second. The coefficient of kinetic friction between the block, right, and the surface, mu sub k, is equal to 0.20. So you're going to have to break this up into like two phases. We're going to have to break it up into the collision phase, and after the collision, the bullet and the block become one, and they're going to move together. So after the collision phase is going to be conservation of energy. Here will be the conservation of momentum. Okay, so the phase one is collision phase. Okay, and this we will use conservation of momentum. Then we will use conservation of energy. Okay. Okay. So there's a friction here that's going to eventually stop this block and the bullet, right? So the final velocity of this is going to be 0. Okay. All right. So the bullet comes to rest in a block which moves 1.8, so it goes from 0 to 1.8 meters before it comes to a stop. All right. So here, for the momentum, conservation momentum, sum of all momentum initial must equal to sum of all momentum final. Initially, I have mass of the bullet times the velocity of the bullet, right? Plus the mass of the block times the velocity of the block, initial, must equal to, right, the mass of the bullet plus the mass of the block, because they become one now, times the V final of the whole system. Okay? Therefore, if I plug in some values, 0.0045 times, right, the initial velocity of the bullet, which we don't know, right, is equal to, well, plus 0, because this is 0, is equal to, right, 0.0045 plus 2.4 times V final of the bullet, and I'm going to say the V final of phase 1, okay? Well, we don't know what this V final of the phase 1 is, but we could probably figure it out using this to figure out what the initial velocity of the bullet in the block is, because we know exactly how much work was done by friction to stop this thing. Okay? So let's take a look at this part right here, phase 2. Okay? And then phase 2 is work done by friction is equal to change in kinetic energy, plus change in potential energy gravitation, plus change in potential energy spring. Well, we don't have any spring involved, so this we don't have to worry about. There's no change in height, so we don't have to worry about work done by, gravity, right? So this is the only thing we have left, and work done by friction, we know it as force friction dot delta x, and that is equal to kinetic energy final minus the kinetic energy initial. We know friction is equal to mu times F normal which is mb plus mb times g times delta x times cosine of 180, because friction is pointing this way, delta x is pointing that way, so they're opposite of one another, so cosine of 180 is equal to 1/2 mv final of phase 2 squared plus 1/2 mv initial of phase 2 squared. Now we already know final velocity of this mass is going to be 0. So this mass here is mb plus mb, right? This mass. So we can actually cancel out. This should be minus, sorry. We can actually cancel out this mass and this mass, and this negative and this cosine of 180. So we have now mu g delta x is equal to 1/2, right, vi of phase 2 squared. Okay? So let's figure out what's going on then. Here, mu, we know it as 0.2, I believe, times 9.8 times delta x is 1.8 is equal to 1/2 times v initial of phase 2 squared. So what is that v initial of phase 2? So v initial of phase 2 is equal to square root of, right, all this mess times 2, right? So 2 times 0.20 times 9.8 times 1.8. All right, so what is that? So it looks like 2 times 0.2 times 9.8 times 1.8. And if you square root that, I get 2.66 meters per second. This initial velocity of phase 2 is exactly same as your final velocity of phase 1. Does that make sense? Okay. So we can say that v initial of phase 2 is equal to v final of phase 1. Okay, we could say that. Therefore, we can utilize this and put that in here to figure out the initial velocity of the bullet. Okay. So here, this is part A, by the way. So here we can say 0.0045 VB initial is equal to, right, 2.4045 times 2.66, right? So if you multiply that by 2.4045 and then divide that by, so VBI is equal to 0.0045, I get 1,419.4 meters per second as the initial velocity of the bullet. So that should be positive. All right. let's take a look at 55. A block of mass M1, 2 kilograms, right? So this looks like the 2 kilograms. Along a frictionless table with speed of 10 meters per second. So initial velocity for mass 1 is 10 meters per second. Directly in front of it and moving in the same direction, the block of mass 2 is 5 kilograms. So this looks like mass 2 is equal to 5 kilograms. Okay, it's moving at 3 meters per second. A massless spring, right, with spring constant K of 1120, right, so this K value is 1120 Newton per meter, right, is attached to the near side of M2, right, as shown. When the block collides, what is the maximum compression of the spring? Wow. Okay, that's big wow. So we got to find out the collision part first to figure out, how much speed it's going to be, right, after they collide together to figure out how much work was done on the spring. Okay, and then because of that, it's going to compress together after the collision. Then conservation of energy must be used after we do the collision part. All right, so we have to figure out what's going on. So when the block collides with the maximum compression of the spring, all right, so here's a hint for you. At the moment of maximum compression of the spring, the two blocks move as one instantaneously, okay, instantaneously. So find the velocity, right, by noting that the collision is completely inelastic at that point, all right? So let's figure out what's going on. So for the collision part, right, we have sum of all momentum initial must equal to sum of all momentum final. Now remember, we always start with this, right? So initially, I have M1 V1 initial plus M2 V2 initial, right? That must equal to, now they are saying treat it like a completely inelastic collision, which means M1 plus M2 become 1 times the V final, right? So here, my M1, which is 2, V1 initial was 10, right? Plus M2, which is 5, times V2, which is 3, is equal to 2 plus 5 V final. So this will be 20 plus 15 is 35 is equal to 7 V final. So my V final is equal to positive 5 meters per second. Well, let's take a look at what's going on. Right? Here, now we have to use conservation of energy. So we can say, since there's no work done by friction here, right? So no work done by friction is equal to 0. Therefore, total energy initial must equal to total energy final. So total energy initial is just kinetic energy of mass 1 and kinetic energy of mass 2. But they're both moving. that has to equal to the kinetic energy of 1 plus 2 when they're together, plus the potential energy of the spring, final. Does that make sense? Okay. So kinetic energy initial is 1 half m1 v1 initial squared plus 1 half times m2 v2 initial squared is equal to 1 half times m1 plus m2 times vf squared plus 1 half kx squared. Whew. We're looking for this x. All right. So let's plug and chug. I mean, I guess we could cancel out all the 1/2s. That's convenient. So here, mass 1, which happens to be 2 kilograms, times 10 squared plus 5 kilograms times 3 squared is equal to 2 plus 5 times 5 squared, right, plus 1120 times x squared. Now, rest is algebra, right? So this is pretty easy. So this is 200 plus 45, right, is equal to, what's that? That looks like 7 times 25, right? 175 plus 1120 x squared. So x is equal to square root of all this mess. So 245 minus 175, divide that by 1120, and I get 0.0625, which comes out to square root of that. I get 0.25 meters as my compression. All right. I'm going to come back to 56 because this really takes a long time to do because you have to go back and forth and back and forth. This cat cannot make up its mind. So we'll come back to this because this really eats up a lot of time. We'll come back to this, and if we don't have time to do this, then I'll post the solution up on Schoology. So this is really just not that difficult, but just tedious and takes a long time. All right, here we go. So here, collision in 2 dimensions. Normally, in a game of pool, a cue ball strikes another ball initially at rest. After the collision, the cue ball moves at 3.5 meters per second along a line that makes an angle of 22 degrees. So this is cue ball right here, with its original direction of motion. And the second ball has speed of 2.00 meters per second, and find A, the angle between the direction of the motion, right? Usually the billiard balls are same masses, okay? So you could assume the masses of the cue ball and the pool ball is the same, okay? So MC is equal to MB, which is equal to M, all right? Find the angle between the direction of motion of the second ball and the original direction of motion of the cue ball and the original speed of the cue ball, and that is the kinetic energy conserved. Usually, you know, we can assume if this was elastic collision, they should go off at 90 degrees. But they never tell you that it is elastic collision, okay? So we cannot really assume that, okay? Uh, so we cannot assume that this is elastic collision because they didn't tell us that, okay? And later we'll probably find out the kinetic energy was not conserved, all right? So we cannot assume that it is elastic. So let's make it inelastic just to figure out what's going on, all right? So if we were to find the momentum both in the x direction and the y direction separately, momentum has to be conserved in the x direction, and momentum has to be conserved in the y direction, no matter what kind of collision it is. Okay? So we have to find the conservation of momentum, both x and the y separately. All right? So let's take a look at the initial momentum in the y direction. So sum of all momentum initial in the y must equal to sum of all momentum final in the y. Initially, this cue ball is moving only in the x direction. So mc vciy is equal to, we're going to have mc vcfy plus mb vbfy. Okay? But here, this is only going in the x direction, so it is 0. Right? So cue ball is only moving in the x direction only. Right? Therefore, we only have these two added together has to be 0. So we know that this billiard ball has negative velocity in the y direction, right? So here we can say the mass times VCY is this. So VCY is 3.5 times sine of 22 degrees, right? So what is 3.5? Well, we could work it out, I guess. So 3.5 times sine of 22 degrees plus m times, this one is negative 2 times sine of theta because it's moving in the negative direction. So notice how the masses can be factored out and then divided to the other side of 0, and they just go away. All right? So we can actually calculate what the theta is. So what is, well, let's say 2.0 sine theta is equal to this 3.5 sine of 22 then, right? So 3.5 sine of 22 is equal to 1.311. Divide that by 2.0 is equal to sine theta. So theta is equal to sine inverse of that, which is equal to, right, 41 degrees. It's like 40.96 degrees or 41 degrees. All right. Well, now we can calculate the x components now, right? So here here, we have sum of all momentum initial in x must equal to sum of all momentum final in x. Initially, I have mass of the cue ball times velocity of the cue ball initial in x is equal to mass of the cue ball times the velocity of the cue ball final in x plus mass of the billiard ball, incident ball, velocity of the ball final in x. So this one is V incident final times 2.0 times cosine of, now we know the angle, which is 41 degrees, right? And this one is V cue ball final x, which is 3.5 times cosine of 22 degrees. Therefore, we can use these in here. And this one, mass of the cue ball again and mass of the incident balls can all cancel out. So the velocity of the cue ball initially happens to be, we don't know, huh? So velocity of the cue ball initial x is equal to, here, velocity of the cue ball final is 3.5 cosine of 22 degrees plus, they're both in the positive x direction, so it's plus. So 2.0 times cosine of 41 degrees. So if you work it out, velocity of the cue ball initial in the x direction is equal to, here I got 4.75 meters per second. All right. So this is part A. This is part B. Now what about part C? Is the kinetic energy conserved? Right? Let's find out. Well, sum of all kinetic energy initial is equal to just the cue ball, right? Times V cue ball initial squared. Really? That's not right, right? No. I was going to say. Which is equal to 1/2 times m times 4.75 squared. So I get 11.28 m joules. We don't know what the mass is, so we're just going to leave it as m. But what about the total energy, kinetic energy final? That is 1/2 m times v cue ball final squared plus 1/2 times m times v incident ball final squared. Therefore, your kinetic energy final is equal to 1/2 times m times your v final is 3.5 squared plus 1/2 m times 2.0 squared. So this becomes 6.125 m plus 2m. Therefore, this is 8.125 m joules. So the change in kinetic energy is equal to, right, the kinetic energy final minus the kinetic energy initial. Right? Therefore, you get 8.125 minus, right, 11.28, right? Okay. I get negative 3.155 m joules of kinetic energy lost. I forgot the m's, sorry. Yeah. Therefore, the collision, right, collision is not elastic. Okay, so kinetic energy is not conserved. All right. All right.
Mr. Kim,
Yeah.
can we take a break?
Yes. Yes, we can actually. Why don't we take a 4-minute break, and then we'll come back. Thank you, Stanley. All right, I'll pause this. So for problem 69, after a totally inelastic collision. Now, when they say totally inelastic collision, means they stick together. Okay, that's what totally inelastic collision means. So when they stick together, they become one, right? So here, initially, I have mass 1, right? They're same masses, by the way. So one's going this way, and then the other one's going this way in the horizontal direction. And you have one that's going vertical direction this way, and the other one's going vertical direction this way, right? And here, this becomes, right, half of the original, right? So if we were to look at the y direction, this angle and this angle are the same angles, right? Because alternate interior angles are congruent. And this angle here is also same as this angle. So if I were to take a look at just the y components, so sum of all momentum in the y direction must equal to, right, sum of all momentum final in the y direction. So initially, I have m times v1 sine of theta 1, right? But this one is in the negative direction, plus m times v2 times sine of theta 2, and this is in the positive direction, so I can leave that alone, must equal to the final momentum is 2m times v final y. But v final y is 0. This is only moving in the x direction. Okay? So we can conclude that since two objects with two initial same mass and initial speed, right, So V1 and V2 are the same, right? So V1 is equal to V2, and M1 is equal to M2, right? So we can say that MV sine of theta 2 must equal to, right? I bring this to the other side, it becomes positive, MV sine of theta 1. This concludes that MV and MV can cancel out. Theta 2 must equal to theta 1. Because if sine of theta 2 is equal to sine of theta 1, then theta 1 has to equal to theta 2. Right? So I'm going to just call that theta. Now if we take a look at the x direction, right? Let's take a look at sum of all momentum initial in the x must equal to sum of all momentum final in the x direction. Initially, I have mv cosine theta 1, right, is equal plus mv cosine theta 2 must equal to m1 plus m2, right, v final, or 1/2 v, right? So here, it looks like I have 2, right, mv cosine theta is equal to 2m times 1/2 v, because v final is 1/2 v. If you want to put i's, you could do that. Okay. So first of all, 2m's can cancel out. VI's can cancel out. Right? So what do I have? I have cosine of theta is equal to 1/2. So theta is equal to cosine inverse of 1/2, which is equal to 60 degrees. That means the angle between them, right? And since they were 60 here and 60 here, so the total angle is equal to 2 theta, which is equal to 120 degrees. All right. All right. 70. Two pendulums, both of length L, are initially situated, okay, as figure drawn here 10-42. The left pendulum is released and strikes the other. So this is just like the Newton's cradle, right? Assume that the collision is completely inelastic, but the difference is they stick together. Newton's cradle, they don't stick together. So again, if it's completely inelastic, that means they stick together and become one. Neglect the mass of the string and any frictional effects. How high? That does not mean that any frictional effects does not mean that this is elastic collision, okay? So don't get that confused. That means they still stick together, so it is completely inelastic collision. So the kinetic energy will not be conserved. All right. So how high does the center of mass of the pendulum system rise after the collision? All right. So we need to think about how much potential energy this thing has that will convert into kinetic energy before it collides. That kinetic energy is going to be the key factor of finding the initial velocity of m1 before the collision. Right? Then once we find that initial velocity before the collision, then we can utilize that as a conservation of momentum for phase 2. That collision part, which is phase 2, will convert now into kinetic energy of 2 masses. Now the phase 3 will be conservation of energy again. So conservation of energy of phase 1, conservation of momentum during collision for phase 2, and conservation of energy for phase 3. All right? So let's start with phase 1. For phase 1, right, just before the collision, I want to find the velocity right before it hits, right? Find the v. That v1, phase 1 final is equal to, right, v2 initial, right? Velocity of phase 2 initial, which is right at the collision, right? So here, we know total energy initial must equal to total energy final. Total energy initial, I only have potential energy gravitation. That has to equal to kinetic energy final. So mgh, right, which is actually d, is equal to, okay, 1/2 mv squared. So this is phase 1 final squared, m1, and this is actually d. So here, my mass 1 can cancel out. So my v phase 1 final is equal to square root of 2gd. Okay? Then, now I go to phase 2. So this is phase 1. Now phase 2 is sum of all momentum initial must equal to sum of all momentum final. Initially, I only have m1, right, moving at v1 initial, right? This v1 initial is equal to v phase 2 initial, right? They're same things. Is equal to, right, m1 plus m2 times v final of phase 2. This v final of phase 2 is equal to, right, v initial of phase 3. Okay. All right, so here I have m times square root of 2gd is equal to 2m times vf of phase 2. So we can say, oh, masses can cancel out nicely, right? Masses can cancel out, which gives me well, let's work it out. So my v final of phase 2 is equal to, right? I guess we can't really assume that m1 and m2 are equal to each other. So let's not cancel them out. I'm sorry. I thought maybe they were same masses, but they're not same masses. We cannot assume that. All right, so sorry. So we cannot cancel out the masses. So we have to say m1 over m1 plus m2 times square root of 2gd. Okay, we cannot eliminate these masses here. So this is m1 and this is m1 plus m2. Yeah, we cannot do that. So this is what we have. Okay? All right. Now the swing part. Here, we have total energy initial of phase 3 must equal to total energy final of phase 3. Initially, I only have kinetic energy after the collision. Afterwards, it's going to transfer over to just potential energy gravitation. So here I have 1 half m1 plus m2 times, right, v initial of phase 3 squared is equal to, right, m1 plus m2 times gh. Therefore, these two will cancel out nicely. Right? So here I have 1 half times, okay, this is that, m1 over m1 plus m2 square root of 2gd quantity squared is equal to gh. So when I square all this mess inside, I get 1 half times m1 squared over m1 plus m2 quantity squared, right, times 2gd, which is equal to gh. G's can cancel out. So my h now is equal to, right? Oh, and the 2's can cancel out. So my h now is equal to just m1 over m1 plus m2 quantity squared. Oh, times d. Whew. All right. Let's take a look at the last page. And then, if we have time, we'll go back to that cat jumping back and forth on the sled. All right, so we have 1 kilogram block at rest. So this is 1 kilogram block. And a horizontal frictionless surface is connected to a unstretched spring. So K value for the spring happens to be 200 newtons per meter. And we have 2 kilogram block whose speed is 4 meters per second collides with 1 kilogram block. So since we have horizontal frictionless surface, so work done by friction is equal to 0. You could imagine what would it be like if there was friction here. We could give you that if you want. So if the two blocks stick together after one-dimensional collision, right? So again, if the two blocks stick together, that means completely inelastic collision, right? What is the maximum compression of the spring occur when the block is momentarily stops? So after they collide, that's conservation of momentum. Now, once they start moving as one unit, now it becomes conservation of energy. Okay, so there are two phases here, right? So phase 1 is conservation of momentum, right, during collision, right? Phase 2 is after collision, right? Conservation of energy, all right? So let's start with the collision part, right? So collision part, sum of all momentum initial must equal to sum of all momentum final. Initially, I only have mass 2 moving at initial velocity, right? Afterwards, I have mass 1 plus mass 2 times V final of phase 1. Okay, so you could say V final of phase 1 is equal to V initial of phase 2, right? You could say that. So here, mass 2 happens to be 2 kilograms times 4 meters per second is equal to 1 plus 2, right, times Vf of phase 1. So here I have 8 over 3 is equal to Vf of phase 1, right? So this is the initial velocity of phase 2. Now we could say, okay, total energy initial must equal to total energy final. Okay. Then here, total energy initial is basically just the kinetic energy of the two blocks sticking together moving as one. That has to equal to just the potential energy of the spring final. There's no height change, so we don't have to worry about any potential energy gravitation. Right? So total kinetic energy initial is just 1/2 m1 plus m2 times v initial of phase 2 squared. That has to equal to 1/2 kx squared. So here I have 1/2 of 1 plus 2 times 8/3 squared is equal to 1/2 times, what's the k value? 200 times x squared. Okay? So this is 3 and this is 3, so 3's can cancel out, right? And then you got a 1, 3 left over here. So 64 over 6, right? So 64 over 6 is equal to 200, actually is equal to 100. So I left it to 1/2 here, sorry. So, or, I could do 64 over 3, 200. So what is my x? My x is equal to 0.327 meters as the compression. All right, this is for fun. What if there were friction starting right underneath this block? Here, no friction. But right here, as soon as they collide together, there's friction. What if mu sub k happens, right, after collision? then what is the maximum compression of the spring? This part wouldn't change, right? Because this friction happens only after the collision. However, we cannot use this. We have to use work done by friction is equal to change in kinetic energy plus change in potential energy gravitation plus change in potential energy of spring. Obviously, that would go to 0. This would have F friction dot X, right, is equal to kinetic energy final minus the kinetic energy initial plus potential energy of spring final minus the potential energy of spring initial. Final kinetic energy is 0 because they'll both come to a stop before they move back out. Right? So instantaneously, they'll come to a stop. Initial spring wasn't compressed, so no potential energy of spring initial. Here, mu times, right, F normal times X times cosine of 180 is equal to negative 1/2 m1 plus m2 times v initial of phase 2 squared plus 1/2 kx squared. Mu times F normal obviously is, so negative mu times m1 plus m2 times g times x is equal to, right? You can figure out the rest, okay? So you're going to probably have to use quadratic formula to figure out the x, okay? So let's plug in some values and set this over to the other side and set it equal to 0. So 0 is equal to, let's put the higher order, which is 1/2 times 200 times x squared. Minus becomes plus 0.3 times 3 times 9.8x minus 1/2 times 3 times 8/3 squared. All right, so 0 is equal to 100x squared, whatever this is, right? 0.3 times 9.8 times 3, like that, plus 8.82x plus, oh, this should be minus, sorry, this should be minus, right, 64 over 4, right? 64 over 6 is equal to 0. So use quadratic formula, okay? And you should be able to calculate x. I have quadratic formula. All right, so please see if you can work on it, and then it's good. It's a good thing. Okay. All right, I'll stop there. Thank you, Stanley, for giving us a break.